Welcome. I'm going to go over some problems to help get ready for your midterm assessment. First off, some thoughts about the exam before you actually take it, and one about the video itself. The first is, when I get to the problems, I recommend that you pause the video and try to solve the problems before I do. While true in all classes, I especially think in general chemistry and some of our early chemistry classes, most of the difficulty is in setting up the problems. The actual math applications and churning through that tend not to be the most challenging parts. It doesn't mean you can't make mistakes there and you don't need practice there, but that usually isn't what's tripping up the majority of students they interact with. Because of this, once you've heard me know how to solve the problem, then you know how to do exactly that question. And so you don't get that practice of, okay, how do I set this up? So I strongly encourage you to try to solve these problems and pause at each slide to do them first, and then watch me do them. If you're not sure how to do it, try to get as far as you can like you would on the assessment to see, are you going in the right direction or not? That's still helpful even if you don't know exactly how to solve the question. Now, a few notes to think about. First, once the exam starts, your goal is to get as many points as possible. There's always a chance I'm going to try not to, but maybe I made the exam harder than I should have. If I do that, and I'll do some evaluations after you get done with the exam, I look through all the scores, I look at what questions people are missing and getting right, seeing if things are appropriately scaffolded out of, like, okay, these questions should be missed by people that make a B but get right by people that make a A or something like that, or they actually make something more difficult than I meant to. I'll go through and look at that, and if that's true, I'll give you a curve. Usually I don't have to, but that has happened before, especially because I write new assessment items regularly, and I could misjudge that. Remember that when you're taking the exam. Try not to let it get too much in your head of just, oh gosh, I missed it. And I say this as a student that totally did these things, right? Like if I get through 2 questions, I'm like, oh my gosh, I bet I already missed 8 points. Oh my gosh, if I miss more than 2, I'm not going to make an A. What am I going to need to make at least to get a B on this? Oh gosh, what is that? And spending all that mental energy on that makes you do poor on the exam. Now, I'll admit, it's easier said than done. You will probably do at least a little bit of that. At least some of you will. Maybe some of you have these wonderful brains that don't pick on you nearly as much as many of us do, and you're just going to be able to not phase all that out. I recognize that happens, but as much as possible, try to let that not happen to you. Also remember, in the case of my assessment specifically, your entire exam grade is not just what you're doing in class, right? You're going to be taking an in-class assessment that is part of your grade, and then you'll be doing an online portion as well. So you aren't getting 100% of the test score sitting down right there. So you still have a chance to get more points if you don't feel as confident as you want to. You've got some time to go back and be like, okay, got another chance at this. So that can help out. Next, make sure you show some work on a problem, even if you aren't sure how to do it. I really would like to give you partial credit for showing me that you've gotten something out of the class. So as long as it's at least somewhat relevant to there. And honestly, even if it just shows a little bit of effort of you took all the variables and correctly identified them and put the values for them to show what mattered in the problem, I can give you at least a point on the question. Do that. Your goal is to get as many points as possible, right? You're not supposed to go, well, I'm definitely make a B because I missed this question. There's no reason in going on. That doesn't help you at all. So get as many points as possible. With that, there are also times where that process of getting started can either help you in ways you don't expect, that you go, oh wait, this is the thing now I remember from class because I tried to do this thing and it feels familiar. That can help you. And sometimes you're closer to the right answer than you think. Like you're like, gosh, I just haven't gotten it. But you've actually gotten through 80% of the problem. You just didn't realize it. So show me those things. If it's just in your head and it doesn't get on the paper, I can't do anything with it. It's also true that if you know a problem really well, you have time on this assessment. Still show me the work for it, because either A, you make a small mistake somewhere, and if I can't see it, you might lose a lot more points for something that's really minor. Like maybe you just used a molar mass wrong, but you were just so sure you didn't even write down that step and show me, and then I'm like, I don't know what you did. You have a really weird number, and it turns out you just reversed a 3 and a 1 in some number and said 130 instead of 310. But if you didn't write that down, I can't tell that. So I can't give you as many points because I have difficulty assessing how much of this have you shown to me. Because my goal in looking at your work is to see this is how you're demonstrating I know how to do these different step parts of this problem. Purposely, the problems you're doing in class have multiple steps to them, and I'm trying to assess each of those parts, not just did you get the correct answer at the end. Also, I won't give full credit for a correct answer with no work shown at all. You have to show some amount of work there because I need to see how you got that. That process is part of it. Note, I am okay if you use a different way to demonstrate it than what I did in class. If you know something from a chemistry class you've learned somewhere else, as long as your assessment is a valid one, it's okay if the work looks a little bit different. And finally, I just want to mention that while I'm assessing what you know, it's part of my job, as something I have to do, you get a grade in the end, that's part of the classes. My goal isn't for you to do poorly. This doesn't mean I will just give you a free grade and I will give you an A no matter what, or pass you no matter what. But I say this because sometimes I know it can feel like your professor is trying to screw you over. Like, at least sometimes, like, most people did, but occasionally I have someone like, you're just trying to mess with me, aren't you? That is not my goal, but I am trying to assess you. For example, I try not to make what I would think of as a trick question, but there are times where I'm trying to differentiate between, hey, do you know this specific subcase of this issue? This is part of the concept. So I may ask questions that intentionally, if you don't recognize something and you answer something else, it shows me you haven't fully grasped this concept. You've gotten the basics, so I can give you some credit, but I have to count off some points because you've missed a part of it. That's the idea of our assessment. Okay, gotten through all my exam strategy thoughts. Let's look at examples now. There we go. Switch back to pen mode. So, as I recommended earlier, I suggest you pause it, try these 3 questions. Now I'm going to solve them because I assume you either paused it or you're just like, I don't feel like pausing. And if you don't, if you at least listen, that's better than not doing anything. So if that's what you do, that's fine too. I still recommend, I think, solving them first is more helpful, but whatever. Let's go. The car travels at 55 kilometers per hour for 36 minutes. How many meters did it travel? So we have our question. We know we want to know how many meters it traveled, and that's my goal. And then we're given a piece of information. We're given a rate. Now, this is an example of a conversion problem where you're using information given in the problem to figure it out. What I like to do is figure out where there are equality statements in questions like this. So this says there are 55 kilometers per hour, and then the traveling time is for 36 minutes. I didn't mean to keep underlining there. So this statement tells me that for every 55 kilometers I travel, I go 1 hour. Note, you can also write this like this, kilometers per 1 hour, or you could put the 1 hour on top, depends on what you need. And so that's my conversion the problem's given me. It has given me a way to take units of time and go to length in kilometers in this case. So I am also given a time. And so this is kind of like some of the other conversions problems, right? Like maybe you get meters to millimeters in a problem, and then you use your conversion for that to go from one to the other. Here the conversion is just given to you. So I'm going to start with my 36 minutes. And because my conversion is in kilometers per hour, I need to get this from minutes to hours to be able to use that conversion. So I know there are 60 minutes in 1 hour. From there, I know that every hour I can travel 55 kilometers. And then finally, the problem asks for it in meters, so I know every 1 kilometer is 1,000 meters. And if I check my units, I'm going to have gone from minutes, which was the starting information I was given. I got rid of hours, got rid of kilometers, and I've got it in meters like I would expect. And so now you multiply the top and then divide by each number on the bottom. Ooh, my room is dark. Just a second, let me pause this. Through the magic of software, it is no longer dark. So now I can see my calculator. So 36 minutes. Also, just to point out, when I talk through this, I'm not going to mention multiplying and dividing by 1. It doesn't change anything. So you're technically multiplying by 36, 1, 55, 1,000, then dividing by 60, dividing by 1, dividing by 1. I'm just going to skip saying the ones because they don't change anything. So I have 36 times 55 times 1,000 divided by 60. From there, I get 33,000, and I should have 2 significant figures in my answer because there are 2 in the time component of my question, which is the least number of significant figures. And 33,000 conveniently does that because remember, these zeros don't count because they're trailing zeros without a decimal place, whereas trailing zeros with a decimal place do count. So this only had 2 sig figs, so we're good to go. So that's the answer to my first question there. Now let's look at the second one. Ace pointer. So how many kilograms of sulfur are there in 22.5 moles of sulfur? So most of this question has 2 parts to it. The first is to recognize what conversion you can use to get from mass to moles. And that's to remind you, you can use molar mass. Your periodic table gives you conversion factors that let you go from grams to moles and moles to grams. So if I look up sulfur on a periodic table, it is 32.06 grams of sulfur per mole. I got that by looking up on a periodic table. You will have that on your exam. So I know 32.06 grams of sulfur equals 1 mole of sulfur. Now, The second part of this question is recognizing you can combine this with the fact that you could do prefix conversions. So I've asked about kilograms, so when you get to grams, you can then go, there are 1,000 grams in 1 kilogram. So I'll start with my starting information. I have 22.5 moles of sulfur. Note, I like denoting not just that it's moles, but it's moles of sulfur, because some problems, especially in the second half of the course, but even in the first half of the course occasionally, at least one test question I'm at least planning for this semester has one where this matters, it's going to matter what your units are of, and you need to keep track of multiple things. And so it's not always going to be sulfur. It might be the problem also included some other things. So keeping track of this as part of your thing helps you to not make mistakes later. So we know 1 mole of sulfur is equal to 32.06 grams of sulfur. Note, I put the moles of sulfur on bottom because I knew I wanted to cancel it out with the numerator here. If the problem had started me in grams, I would use my conversion the other way, and I would have had grams on bottom. So there's not something in my head that just says always put mole on bottom or always put mole on top. It is I put on bottom what's going to cancel out with the units in the numerator of earlier in the question. So I'm always choosing my units based on what cancels earlier in the problem. So this will get rid of moles. And then since the problem gave me a specific unit for mass, I've got to convert to that. And there are 1,000 grams of sulfur in 1 kilogram of sulfur. And another good reminder is that for counting significant figures, my conversion factors, like 1,000 grams of sulfur equals 1 kilogram of sulfur, are treated as having infinite significant figures because that's a rule. That's an exact number. There are exactly 1,000 grams in 1 kilogram. It's not a measurement where you could be off a little bit. So I'm limited by significant figures, by my moles of sulfur. That is 3 significant figures. My answer will have 3. So I have 22.5 times 32.06 divided by 1,000. And my calculator says 0.72135, so I will say 0.721 kilograms of sulfur to correctly round to 3 significant figures. That's the answer to my second question. Let's go to the third one now. And there we go. How many atoms are there in 0.228 moles of iron atoms? So this is an example of a question that gives slightly more information than you need. So it tells you the fact that these are iron atoms. That's not going to come into my problem at all. I want to point this out, not because I think this is a super hard question, but because it is easy as a student to get sort of metagamey and be like, Dr. Leslie said it was iron, it must matter, I must use a molar mass. No. So because it is very practically realistic, you will oftentimes have more information than you need in like an actual problem. I'll know all kinds of stuff. And it is my job as a student or a chemist or whatever I'm doing to isolate what parts matter. I will sometimes give you more information than you need because I think that is a good practice into it. It is good at assessing your ability to pick out what matters versus what doesn't. So this is intentional and is not to like just, it's not like a trick question to mess with you. That's not the goal. The goal is to see, can you realize the fact that this says iron atoms doesn't matter. I could say chlorine atoms. I could say 0.228 moles of any type of atom, and the answer would go the same way. So this is just making sure you remember a conversion that we haven't used as much in class as some of our others, but if I have moles, I can convert that to just straight atoms by remembering that 1 mole is 6.022 times 10 to the 23rd of that thing, in this case, atoms. And so I've got 0.228 times 6.022 times 10 to the 23rd. And from there, I will get I've got 3 significant figures, 1.37 times 10 to the 23rd iron atoms. And that's my answer to my third question. So let's move on to some more examples now. Again, that's just pausing, try these out. Now I'm going to go over them. So first I have what is the mass of 1 mole of CH4? 1.00 moles. Either way, that works. So this is about making sure you can identify how to calculate a molar mass. And in this case, it'll be easy because it's in 1 mole, but I'm going to go through and solve it like it was any other number because that would depend on it. So like it would change, that could be part of it. So if it was 2 moles, you'd have to do an extra conversion to count for that. So I'm going to solve it like it were a number other than 1. So molar mass, remember you take each atom and add up its molar mass, and you jam them all together, that makes the molecule. So we have 1 carbon atom that has a molar mass of 12.01 grams per mole. We add to that, we have 4 hydrogen atoms that each have a molar mass of 1.01 grams per mole. When I add those all together, I get a molar mass of 16.05 grams per mole, if I can do math in my head correctly. I think I can. So I now know that for every 16.05 grams of CH4, there's 1 mole of CH4. Remember, this grams per mole, or any of these things where I've got one thing divided by another, is a way of talking about a rate. So in this case, for every mole, I have 16.05 grams. So I can rewrite this as an equality statement. So 16.05 grams of CH4 equals 1 mole of CH4. And so that gives me two fractions I can use. I can put the mole on bottom or top. Now I'm going to set this up, assuming that I had to. For the purpose of a test, if you recognize you don't have to do this last step, you can go, oh, it's 1 mole. That means it's 16.05 grams. I'm done. But in case you didn't, or in case it was anything other than 1 mole, then I would set up like this, 1 mole. And then for every mole of CH4, I get 16.05 grams of CH4. Now, there's one statement I misspoke a little bit on, the fact that 1 doesn't matter. It matters a tiny bit in the sense of it determines your rounding. So 1 mole times 16.05 grams per mole will give me 16.1 grams of CH4. And that would be my answer. I'll make a quick aside. Note, you don't have to answer this on the test. If you were to tell me this is 16.0 grams, I would also give you credit. Technically, that's a better way to round this. There are some rounding rules we don't talk about if you have things that end exactly in 5 and there's nothing after them. So if you know rounding rules that have been taught more carefully and you know to do that, that's fine. Having said that, if what I just said is like, what do you mean I round it to 0? Why would I do that on a 5? Don't worry about it for now. I talk about my analytical chemistry course, and if you go, you know, read how to round 5s. If you put it in Google or some search engine, you'll find an answer to that. But it's not important for the assessment. I'll give you credit for 16.1. But if you were more correct in what you're doing, I'm not going to count off for that. So if you already knew that, and you put 16, I'll give you 0.0. I'll give you credit as well. Next question. What is the frequency of a light wave if its wavelength is 225 micrometers? So this question really has two parts to it. One is making sure you know how to get between frequency and wavelength. The second is making sure you know what a micrometer is, because that's probably the prefix we've used the least in class, and so it's less familiar, that or nano. But we use nano a lot in wavelengths usually rather than micrometer because nanometer is visible light, so this is probably the least used. So step 1, I'm going to convert to meters because that's what unit I'm going to have for the speed of light. You could also convert speed of light to micrometers per second. That's not wrong, just less common of a strategy. But it's fine. But I'm just going to convert to meters because I like working in base units. It just feels good. So 225.0 micrometers. There are 10 to the 6 micrometers per 1 meter. And so that means, okay, because people are watching, I'm going to put this in a calculator. I really think I know how to do this in my head. But I also know that I forget how to do everything once I'm in front of a camera. 2.25 times 10 to the negative 4th meters. There we go. I think I could have gotten that. Now, quick aside. If you did this and you got, there's something I'm going to do wrong on my calculator on purpose. I'm trying to remember what it tells you. If you got 2.25 times 10 to the negative 5th, it means you are putting scientific notation in your calculator in wrong. What you are probably doing is for this, you are putting in 10 E6. The problem is that E represents times 10 to the 6th power. So that statement means 10 times 10 to the 6th, which is 10 to the 7th, not 10 to the 6th. So if you want to put in exactly 10 to the 6th, you would literally just put E6. And you'd be good to go. You don't have to put a number in front of it, or if it makes you feel better, you could put 1 E6, 1 times 10 to the 6th. Either works. That's a common mistake SC students do. Now, if you use your calculator a different way and you put times 10 to a power, as long as you're using parentheses doing correctly, that's fine too. Just wanted to highlight this because I see this error and it bugs students. I know when it happens because it's hard to Google that thing. It's like, why did that do that? You don't know what question to ask. Hopefully I help somebody that watched this video not do that again. Okay. Through that, we've got our wavelength now in meters. Now we can plug it into our speed of light, or our equation to get between frequency and wavelength. As a reminder, the speed of light is equal to wavelength times frequency, wavelength being the first symbol, frequency being the second. That's a lowercase lambda, lowercase nu. Best I can draw them at least. I'm going to rearrange this because I know wavelength but don't know frequency. I'm going to do C divided by wavelength equals frequency. And now I just plug these in. The speed of light is 3 times 10 to the 8th meters per second. Note, if you know this to more significant figures and you put in a more correct answer for the speed of light, like 2.99, I forgot what the other digit is off the top of my head, which is embarrassing. I should know that. But if you do that, that's fine too. But this will be good enough for this. 3 times 10 to the 8 meters per second, and then divided by the wavelength, which is 2.25 times 10 to the negative 4th meters. Notice the meters cancel, which is good. So I'm left with the right units. So I have 3 times 10 to the 8th divided by 2.25 times 10 to the negative 4th, and I almost copied my wrong answer from my calculator. There we go. When I do that, I get 1.33 times 10 to the 12th, And there's a few different ways to write this. So this came out as 1 over seconds. That's fine. You may also see it written as s to the negative 1. You might finally see it written as hertz, which is our name for this unit 1 over seconds. All three of those are fine answers, and our multiple choice, you should recognize all of them. They shouldn't make you panic. You should be able to go between them, but they all mean the same thing. So that's the answer to the second question. We've got one more to do now. Erase. And there we go. If the density of an iron cube is 3.50 grams per cubic centimeter, has a volume of 25 milliliters, how many dollars would it cost if the iron was valued at a price of $2.50 per mole? This is just an example of a problem that has multiple conversions you have to do. It also has a few other pieces of information it wants you to know. So it wants you to recognize that a cubic centimeter is equal to 1 milliliter. Those units are the same. That's one of the other things other than the prefixes I've asked you to have memorized. And that's just because different ways of measuring volume tend to give different units, or when you're looking in different contexts, you'll see both. So you need to be able to know that those two are equal. So we could have also said the density is 3.50 grams per milliliter. You get the same answer. So that's the first thing to note. The other is to recognize how to deal with the idea that we have an extra thing thrown in here about cost, right? So so we've been given a density and a volume. We can use that to find mass. But we're also told the iron is priced at $2.50 per mole. So that means every $2.50 of iron is equal to 1 mole of iron. So that means I want to get to moles. Because I get to moles, I can get to cost. And that's the idea of a lot of these conversions, right? Sometimes you'll have some additional information. So this problem told you, hey, if you get to moles, we've got another step to do. So I need to get to moles. Moles are my common in-between unit. And the best way that I know currently in the class to do that is to use molar mass. That lets me get from grams to moles. That's my way to go from mass to moles. And in this case, I can find mass because I know density. And so density lets me convert between my grams per cubic centimeter and my volume. So let's start with my volume. I have 25.0 milliliters. 1 second. So we've got our 25 milliliters. I flipped my pen around so it's backwards. There we go. So we know that every milliliter is a cubic centimeter. And we've got a density. This density, remember, is we've got this slash mark here. So that's a way of saying 3.50 grams is equal to 1 cubic centimeter. And it's 1 because there's no number in the denominator, so it's got to be equal to 1. So I put 1 cubic centimeter on the bottom to cancel those out, and then I've got 3.50 grams. And that's grams of iron. So now I've got rid of my volume, and now I'm in mass. But I want to be in moles. So my periodic table shows me that for every 55.847 grams of iron, I have 1 mole of iron. So that'll get me to moles. And then finally, the conversion I was given in the problem, for every mole of iron, it's going to cost me $2.50. So let's see. I've got 25 times 3.5 times 250 for the numerator, then divided by 55.847 for the denominator. And this is going to cost me $3.92. So that is the cost of my iron. Okay, I've got some additional problems. I'm going to stop here, and then I'm going to make another video to cover the rest of them.